The interstellar void is deep and black as eternity, but scattered through it are worlds that burn with their own quiet fire. Not every world needs a sun to shine. In the vast reaches between stars, a strange kind of world drifts alone, unlit, unanchored, and untethered to any sun. These are the rogue planets, wanderers of the void, cast adrift through cosmic misfortune, or possibly born that way, in the cold interstellar wilderness. Today, we are returning to a topic we explored years ago, but with sharper eyes and broader horizons. Back then, we considered rogue planets mostly as a curiosity, a scientific puzzle, or a doomsday hypothetical, but a lot has changed since then. Not only have we learned more about how common these worlds might be, but we've also deepened our understanding of how life might survive on them, and how we might one day call them home. This is Outward Bound, our series on how humanity might colonize the toughest, weirdest, and most extreme places in the cosmos, and rogue planets might just take the crown. No light, no sunrises, no seasons, just a frozen sky and whatever warmth you can bring with you, or dig down to find. In the interstellar night, warmth is a treasure, and pressure is life. Survival doesn't begin with oxygen or sunlight. It starts with shelter from the void, and enough energy to keep the blood moving and the machines humming. But even in the deepest dark, possibilities persist. Some of these worlds may harbor hidden oceans warmed by internal fires, or thick atmospheres of hydrogen and helium insulating seas of exotic liquids. Others may be mass enough to attain their moons, even build entire ecosystems beneath layers of ice or gas. And with the right tools, fusion power, megastructures, and a little audacity, we might not just survive on these lonely planets, we might thrive. So what exactly is a rogue planet? How many are out there? And what would it really take to build a civilization on one? Let's begin by charting the territory. What are rogue planets? Rogue planets, also called interstellar planets or nomads, are planetary mass bodies that drift alone through space, unbound by the gravity of any star. They don't orbit anything. Instead, they wander the galactic void, tugged along by the gravitational tides of the Milky Way and the occasional passing star or molecular cloud. Unlike the icy rubble of the Kuiper Belt or Oort cloud, rogue planets are fully fledged worlds, ranging from frozen rocky dwarfs to gas giants and even brown dwarfs, though our focus today isn't on those substellar objects, except insofar as they might have moons, as could any rogue world in the Earth, Mars, or even Pluto size range. These lonely wanderers may seem like rare cosmic accidents, but modern surveys and simulations suggest they could be shockingly abundant. While early estimates hinted at 1 or 2 rogue planets per 100 stars, new data from microlensing surveys, such as those conducted by Ogle or Moa, suggest the real number could be far higher, maybe even 1 or 200 per star. That means there could be tens of billions to hundreds of trillions of rogue planets drifting through the Milky Way, vastly outnumbering the stars themselves. Much would also depend on how we counted them, in terms of minimum size threshold. By and large, we find that the frequency of celestial bodies has an inverse relation to size. Something several times larger is several times less frequent, and smaller things several times more common. So far from being outliers, they might be the hidden majority of planets in our galaxy, dark, silent, and waiting to be found. But how does a planet become a rogue? Some are likely born that way. In the early days of star and planet formation, chunks of gas and dust collapse in massive bodies before a star fully ignites. In dense stellar nurseries, some of these clumps never end up in orbit around a star at all. Instead, they form planet-sized objects that never knew a sunrise, drifting away even before the local stars have settled down. Others are castaways, exiled by violence. In young solar systems, chaos is the rule. Massive planets jockey for position, gravitationally shoving each other into new orbits, gaining and even losing mass, as some theories now predict Jupiter might have been twice as large in the past and migrated closer to the Sun than far away again. One close pass too many, and a world can be flung outward with enough speed to escape its star entirely. This process, known as planetary ejection, may have played out in our own system. Some models suggest our early solar system once hosted additional objects, super-Earths or Neptunian-class worlds, now long gone. And again, we believe there's a good chance Jupiter migrated and disrupted the early solar system, and we likely passed very close to other stars in the past too. So beyond the larger moons that the gas giants have accumulated, many early planets in our solar system may have merged, as we think happened with the Earth to form the Moon, being swallowed by bigger planets or the Sun, or been ejected into the deep void, likely all of the above and several times each. Stellar encounters add to the drama. A passing star, brown dwarf, or even rogue planet itself might drift close enough to destabilize a system, yanking a planet free. And while such flybys are rare in the modern era, over billions of years, near misses accumulate. We believe Source's star passed into a light year from us as recently as 70,000 years ago, and that Gliese 710 may pass as close as 22 light days from us in just over a million years. And remember, Earth is 40,000 times older than that window of time between those two close passes, so it wouldn't be hard to imagine we've had a lot of closer calls, especially during more disrupted periods in our galaxy, which is prone to eating smaller ones. The Milky Way is a crowded place, and planetary orbits are not eternal. Ejection can also result from binary star systems or from long-term gravitational tugs, like a cosmic tug-of-war between giant planets and moons. These gentle but relentless forces can shift orbits over eons until one body gains just enough energy to break free. This process is slow, but it is inevitable for some systems, especially those packed tight with large bodies. A lot of stars begin their lives in star clusters that slowly disperse, and typically after planetary formation is well underway. Needless to say, a world kicked into the abyss doesn't stop being a world, it just becomes a very lonely one. But lonely doesn't mean lifeless or useless. These orphan planets still carry mass, materials, and sometimes heat. And if they are big enough, they may retain thick atmospheres or buried oceans or moons. They may even offer us a foothold among the stars. That foothold is our main interest today, where even small dwarf planets might make exceptional colony sites to bridgehead us to bigger systems. But while that would still be bringing life to dead and frozen worlds, it may already exist on some. So next, we will explore the conditions that make life on a rogue planet possible, and what kind of alien ecologies might evolve in the dark. Life in the dark. Rogue planet biospheres. At first glance, a rogue planet seems like the last place you'd expect to find life. Drifting through the interstellar void, it receives no starlight, no warmth from the sun, and little more than cosmic radiation and distant starlight to illuminate its skies. The surface might be hundreds of degrees below zero, with atmospheric gases like nitrogen and oxygen frozen into snow or ice. It might even have seas of liquid hydrogen to helium floating on top. But dig a little deeper, literally, and things begin to warm up. We've examined some scenarios for ultra-core biology too, such as ammonia-based life forms, see that episode, and so the worlds might not need to warm up that much. The most likely candidate for life is the Steppenwolf planet, named for its lone wandering nature. The animal, not the band, though both fit. These are Earth-sized or larger worlds with thick ice shells trapping subsurface oceans heated by geothermal energy. On Earth, life thrives around hydrothermal vents deep beneath the sea, entirely cut off from sunlight. It's even the lead candidate for where life first emerged. The same kind of ecosystem could develop on a rogue world, especially one with ample internal heat from radioactive decay, remnant core heat, or tidal forces from captured moons. Remember that even 4.5 billion years after formation, Earth's own core is still hotter than the surface of the Sun. Even ignoring radioactive decay or tidal forces from the moon, a planet can retain heat in its lower levels for a very long time, especially bigger ones, which will generate much more heat from their higher gravity exerting itself on objects falling into form it, and thus hitting faster and with higher energy the more mass it gains. There's an old fantasy series, the Deathgate Cycle by Margaret Weiss and Tracy Hickman, best known from the Dragonlance series, that explores some very novel world building, including a classic Dyson sphere, which I read when I was young and always stuck with me. Each book explores a new and very strange world, and we also see one where life lives in the tunnels of a large rock, maybe planet-sized, and whose surface is cold, but whose center is heated and lit by magma seas, and the population lives and farms those subterranean caverns between them. We also get to explore a world with floating continents and another with asteroid-sized buoyant bodies drifting around inside a vast ocean, like a water world or maybe even a subsurface sea like we might encounter on rogue planets, or their moons for that matter. I ended up rereading the series in the month between when I wrote this and recorded this episode, and it's still a good read. Going back to moons around rogue planets, many icy moons in our own solar system like Europa and Enceladus are already considered prime candidates for life thanks to these tidal force conditions. A rogue Earth planet would simply be a scaled-up version, perhaps with more geothermal warmth and a thicker blanket of ice and gas to retain it. And unlike Europa, it might hold a true atmosphere for a while longer, especially if it retains light gases like hydrogen or helium, creating a powerful insulation effect that helps preserve liquid water below. If a rogue planet has enough mass to retain a hydrogen atmosphere, it could trap geothermal heat far more effectively than Earth's nitrogen-oxygen mix, creating a greenhouse layer where heat lingers far longer and ice melts deeper. Some theorists have even proposed that such planets could host life adapted to very dim light or even infrared radiation. If geothermal energy escapes through cracks in the ice, it could allow for bacterial life that feeds on heat gradients or chemical nutrients, a form of chemosynthesis rather than photosynthesis. Indeed, it's possible early life on Earth might have used this strategy or a similar one. Life here would be slow, sparse, and hardy, more akin to extremophile microbes than bustling ecosystems, but would still be life, potentially with its own evolutionary history, billions of years in the making. We'd also imagine rogue gas giants with captured moons forming entire miniature solar systems of their own. These moons might experience tidal heating, ice layer tectonics, or magnetospheric interactions that mimic the Jovian system. If one of those moons had water, organics, and heat, it might not matter that it's a billion kilometers from the nearest star. And while biology might get stranger in the dark, it would not be impossible. Life may adapt to survive in sub-freezing ammonia slush, or even swim in liquid hydrogen oceans at supercold temperatures, though these would be truly alien environments where familiar rules might not apply. That kind of exotic chemistry is largely speculative, but if nature has taught us anything, it's that life finds a way, especially where there's energy and stability, however meager. Moreover, what evolution might have a hard time making, we can perhaps forge ourselves. I tend to assume humanity will often engineer life forms from scratch to inhabit worlds where we plan to have a presence inside para-terraform structures, but might find it cool to create giant kraken that could dwell in liquid helium seas. Because who wouldn't want to ride a helium kraken into battle across a slush sea? Rather than just adapting humans to these worlds, we might tailor whole ecosystems, extremophile crops, deep burrowing livestock, or luminescent lichen forest, crafted to thrive in the shadows and cracks of alien stone. So while we've yet to find confirmed life beyond Earth, and for astronomical reasons tend to focus on Earth-parallel planets in traditional habitable zones, they'd be easier to detect biosignatures on, not to mention find in the first place, rogue planets may ultimately be some of the best places to look. They are quiet, cold, and shielded from many of the chaotic processes that batter habitable zones around active stars, and if life can persist there, or begin there, then colonizing such worlds may not just mean building bunkers, but cohabitating with something that's already home. Of course, even if no life exists, that doesn't mean a rogue planet is useless. Quite the opposite. They may offer humanity the raw materials and protected environments needed to build civilizations from scratch in the deep void. So up next, let's look at the kind of habitats we might build on these worlds, from buried cities beneath the ice to floating settlements on seas of liquid hydrogen and helium. Settling the shadows. Habitats on rogue planets. When colonizing rogue planets, our first challenge is the lack of sunlight. No solar power, no day-night cycles, no heat from a parent star. But that doesn't mean no energy or no options. No light? No problem. We've brought fusion and fortitude. A rogue planet's surface might be lethally cold, but just below that frozen crust, heat can still be found. And with modern technology, or the help of fusion reactors, we don't have to settle for mere survival in bunkers. We can build thriving settlements, whether beneath the ice or floating on alien seas. We should also be mindful that if these rogue planets are relatively common, several or more per star system, then it's very likely these would make excellent waypoints between star systems, and likely not ones with tiny populations either, at least by modern standards. Many a great empire might begin on such frigid planets and still climb its way up the Kardashev scale, though it may need to begin that climb from deep below the surface. Space travel and strange new worlds are thrilling to imagine, but as we've seen time and again, reaching them often depends on mastering the small, precise, and practical details. Even something as simple as stepping onto the surface of a rogue planet could be deadly if your boots aren't engineered right. Hundreds of degrees hotter than the frozen gases beneath you, they might cause the ground to erupt. In environments like that, every system, from your airlocks to your shoelaces, needs precision you can bet your life on. Now, most of us won't be trekking across icy exoplanets anytime soon, but precision still matters here on Earth, especially in the tools we use every day. Take shaving. Most razors these days are designed around marketing, not performance. But Henson Shaving takes a different approach. They manufacture their Henson razor in an aerospace machine shop, the same kind of place that's built parts for Mars rovers and the International Space Station, because they've actually done both. The result? A razor so precisely made that the blade extends just 0.0013 inches, less than the width of a human hair. This limits blade chatter, giving you a smoother shave with less irritation. I've been using safety razors since my army days. I switched to Henson a couple years back. Their AL-13 is the best razor I've ever owned, and it looks and works as good as the day I got it. Plus the blades are standard double-edge, recyclable, and cost about 10 cents each. No plastic, no cartridges, no nonsense. So if you're ready to stop overpaying for less and get a razor engineered like a spacecraft, visit hensonshaving.com/IsaacArthur and use code IsaacArthur at the checkout to get a free 100-pack of blades with your razor. That's precision where it counts. No planetary landing gear required. Buried cities beneath the ice. One of the most straightforward options is to dig in. On many rogue worlds, specifically Steppenwolf-class planets, the upper layers may be frozen solid, but beneath the crust lies potential warmth, either from geothermal activity or the residual heat of formation. That heat can be used to melt chambers, tunnel networks, or entire cavern systems, turning a planet's icy shell into a fortress against the void. And all that mass and cold makes a good way to hide your waste heat and other technosignatures that might reveal your presence to others. We are growing ever closer to being able to make super strong materials like diamond and graphene at bulk levels needed for construction. I would not be surprised if diamond windows or domes were a real thing even this century, and such materials, made from hyperabundant carbon, might let you comfortably stick a city tens of miles below a frozen surface or sea. Beyond being a great place to stay warm and have access to vast amounts of mineral resources and fusion fuel to power things, this is also a great place to hide from enemies or resist attacks. One could imagine star systems subsidizing icy fortress worlds on their outskirts, who could serve as fleet bases and monitors, and who an enemy could not risk bypassing, much as was the case for castles in the past, for fear that if they did bypass them, that fleet would erupt from their buried bunkers and chase behind them. And as we discussed in our space warfare episodes, a pursuing spaceship has a huge advantage in a stern chase over those they are following. For this reason, we might see every rock big enough to support a base get one, not simply true rogue planets, though they would be far more prized they would support far greater cities, economies, fleets, and populations. We might imagine vault cities, circular hubs entrenched kilometers deep, their walls lined with insulation and radiation shielding, their ceilings glowing with artificial sunlight, powered by reactors humming in nearby cores. Vertical farms could grow algae, fungi, and engineered crops in stacked tiers, while waste heat from fusion plants keep the local environments temperate. Fungi, not crops, might dominate early food production, especially in geothermal greenhouses, where low light and high humidity are ideal for mushroom-based agriculture. Some habitats might be situated near volcanic hotspots or under frozen oceans where geothermal vents do most of the heating. Others might utilize permafrost delamination, a method of gradually thawing and expanding icy tunnels as infrastructure develops. It wouldn't be glamorous at first, more submarine than space opera, but over generations such cities might become cozy, complex, and even beautiful. Crystal caverns, mushroom forests, or vast artificially lit chambers full of terrestrial life, and on the lower gravity walls, embedded O'Neill cylinders sheltered by the ice, with tunnels extending from the centers of the cylinder caps, leading to neighbors you could walk or float between. These settlements wouldn't just be survival bunkers, they'd be cultural seeds, home to music, children, books, and cathedrals, all quietly growing in the belly of a dead world. Floating cities on cryogenic seas. And then there are the surface seas, oceans of liquid helium or hydrogen that might form under high pressure and the right atmospheric conditions. While exotic, they are not purely theoretical. Rogue gas giants or super-Earths with dense atmospheres might trap enough heat to maintain such strange bodies of fluid. Colonizing them would be a challenge, but also an opportunity. Imagine city ships designed like gargantuan Arctic oil platforms, floating on a lake of liquid hydrogen at just 20 degrees above absolute zero. Their hulls would need to be made of materials that don't become brittle at those temperatures, likely layered metamaterials or exotic carbon composites. The air above might be breathable inside domes, but everything outside would be coated in frost, constantly protected from atmospheric leaks and structural cracking. Water is common everywhere in this universe, and even if it were ice deep below hydrogen or helium seas, oxygen leaking from the cracks into your habitats would often end up bonding with that hydrogen. These cities might hover just above the liquid using magnetic repulsion, superconducting skates, or even self-repairing rafts that float due to the density differential with whatever cryofluid lies beneath. We have many superconductors that function at these temperatures and even quite a lot higher. Liquid helium is about an eighth as dense as water, and liquid hydrogen about half that, so while it is still much easier to float in or above than air, you do need to go a lot less dense than a traditional ship or submarine on Earth. As is often the case, scale helps here, as a vast dome mostly full of air could still easily float on such seas, even if it had meter-thick bottoms and walls and domes, providing soil and insulation, and a lot of interior dirt and water landscaping. Some might harvest the surface liquid as fuel, deuterium for fusion, or helium-3 for more exotic reactors. Others could simply treat the surrounding sea as an insulating buffer, keeping the city warm while drawing power from within by conventional fission reactors or some other power source. Such colonies would feel more alien than any lunar base. The sky would be a pitch-black dome, the surface shimmering like frozen mercury, the city glowing like a hearth in an endless winter. And just as we dream of cloud cities on Venus or aerostats and gas giants, these rogue world flotillas could become symbols of defiance, proof that even in the coldest parts of the universe, life can float. Mobility and expansion, connecting the cold frontier. Colonizing a rogue planet might begin with a single buried settlement or floating city, or even an orbital habitat hovering at geostationary and connected to your alpha site by a space elevator. But sooner or later, expansion becomes necessary, whether for growth, redundancy, or sheer curiosity. Fortunately, while these worlds are cold and dark, they offer stability. With no shifting seasons, minimal tectonic activity, and no solar radiation storms, infrastructure can be remarkably long-lasting if built right. With less tidal stress from the sun and moon, seismic activity might decline over time, stabilizing long-term infrastructure and making it easier to build enduring underground megastructures. Surface travel would be slow at first, likely reserved for robotic drones or sealed transports following preheated tunnels or rail corridors carved through the ice. Magnetic levitation trains, supercooled superconducting conduits, or good old-fashioned pressure-protected freight crawlers could move people and goods between outposts. On large rogue planets, we might even see circumplanetary rail lines, arteries of civilization through a world otherwise silent and still. On smaller ones, we might cut shafts directly through the lower layers or even the core itself, which might also provide power and mineral wealth. Power would flow along these veins too. A well-planned colony network could transmit energy from major fusion plants to distant outposts via superconducting lines buried in the ice or rock. Waste heat would be reclaimed to keep pipes and pressure domes warm, recycling energy like blood in a body, or each outpost might be independent, drawing fuel from the local ice, mining fusion materials like deuterium, or cracking oxygen from frozen CO2 or water reservoirs. A rogue planet might be dead to the eye, but underground it could pulse with life. Vibrant civilizations or engineered ecosystems, or even crazy cults or pirate bases, hiding from the outside cosmos. And if these worlds are common, as current evidence suggests, then it is not hard to imagine a whole network of rogue worlds. Some might have multiple colonies, others might serve as fuel depots, military stations, or scientific archives. Traveling between them would not be easy, but compared to the vast gulf between stars, a chain of rogue planets only light months apart could be navigated like lonely islands in a dark ocean. Over time, such worlds could even become the backbone of a slow interstellar expansion, what we call colonizing, should faster types of travel not become practical. Rather than leaping from star to star, humanity might march across the galaxy one rogue world at a time, not colonizing the light, but mastering the dark between it. Out of the darkness, a future in the void. Rogue planets are, by their nature, places of silence and solitude. There are no sunrises, only the soft glow of distant stars and the quiet hum of machines keeping life alive, but perhaps that's part of what makes them so compelling. These worlds are without light, but not without hope. They could be monasteries of the future, places of retreat and reflection, far from the noise of civilization, or they could be the fortresses of survival, built to weather cosmic catastrophes and preserve humanity through the eons. Maybe both. And perhaps they're not the backwaters of interstellar civilization, but its backbone, rugged, self-sufficient, and strategically vital. The relay points of vast interstellar laser highways, pushing ships to near light speed or slowing them down from it as they travel unrestrained by the tyranny of the rocket equation, those beams powered by fusion reactors running on the near endless seas of fusion fuel such worlds would often contain. A civilization that masters the rogue worlds won't just survive in space, it will thrive in the most hostile corners. The people who call such worlds home would grow up without ever seeing a blue sky, except for those they build. Their legends might speak of stars the way we speak of mythical golden ages, and when they finally journey outward to find them, it won't be as wide-eyed explorers, but as hardened pioneers, heirs of the deep dark, bringing with them the knowledge of how to build light where there is none, torch-bearer fleets. And it is worth remembering, these planets are not just potential homes for us, they may already be home to someone or something else. Life does not ask for comfort, it asks only for time, energy, and persistence. And rogue planets offer all three, in strange and subtle ways. If the galaxy harbors ancient intelligences, or forgotten biospheres, simple biologies, or massive post-biological entities, calculated away in the cold hidden depths, it might not be the bright stars we should search, but the lonely shadows drifting between them. Rogue planets are reminders that the universe doesn't offer us a warm welcome, but that hasn't stopped us before. We'll bring our own fire, our own future, and write our legends, even in the dark.